So to begin with, we're going to be looking at quadratic functions for the next week or two. But just generally speaking, what a function is a relationship between variables, where you put a value of one variable into the function, and what comes out of the function is the other value for the other variable. We usually use x as what goes in and y as what goes out. If you like, you can think of a function, although this definition is very limited, you can think of a function as being something you can graph. Not everything you graph is a function, and you learn about the difference between relations that are functions and relations that are not functions last year in Math 10C. Do you recall that vertical line test where if you can draw a vertical line that cuts a graph in more than one place, it's not a function? How many of you had Miss Allen for 10C last year? Did she still show that video of the function notation with the meat going in the factory, the cows going in, and then the steaks coming out? That's what a function is. It's something that takes an input and changes it to an output. But we're going to be looking at quadratic functions, and there's going to be a lot of terminology today. And it isn't that I would ask you on an exam, what does this word mean? Or what does that word mean? It's that if you don't understand what the words mean, you don't understand the questions that are going to be asked. And we're going to be describing how we can obtain graphs of quadratic functions by starting with this quadratic function and transforming it. And transforming a function means to change it through a series of things that you actually learn about in junior high. Reflections, stretches. I think in junior high you call them slides. Does that ring a bell, that you take a graph and you just slide it across the axis somewhere? We use more sophisticated terminology that we'll get to today. So to begin with, a quadratic function is any function that can be written in this form. And when we talk about functions, we talk about variables. In this equation that I have up here, f of x is a variable. X is a variable. And it's more complicated than this, but how many of you remember from last year what f of x is? It's y, right? And what we do as Math 10C teachers is we say, well, it's really quite confusing, so we're going to tell the students, you know what f of x is? It's just another way to say y. If it were that simple, we wouldn't need f of x. Okay, that f brackets x means f of x. It means a function of x, and it means that x goes into the function, and what comes out is f of x. So for that reason, I'm just going to say that a quadratic function is any function that can be written as y equals that thing. So what do we have? We have y, which is a variable. We have x, which is a variable. And I have three other letters. Well, those are parameters. This is very, very similar in mathematical structure to this from the very first unit, where we made a big deal, or I made a big deal of saying that these two things n and tn are variables, right? These are variables. And we even talked a little bit about the fact that sometimes we like to explore what the pattern looks like by plotting tn here and n there. But we made a big deal of saying that T1 and D are parameters. It doesn't matter which point you're talking about on this graph. T1 is the same for all of them, and D is the same for all of them. Good afternoon. Well, the same thing is true here, that we're talking here about variables that are x and y. And these other things are parameters. So if we learn that a particular graph that is a quadratic function, if we learn that a particular graph looks like this, and we will, some of the quadratic functions look like that, then that graph has different values of x and y for every single point of the infinite number of points, but that graph has one value of a, one value of p, and one value of q. And it's those parameters that tell us about the graph. It tells us, those parameters, how tall the graph is, or how skinny the graph is, or how wide it is. There's lots of ways to describe that. It tells us whether the two arms go down towards the floor or up towards the sky. It tells us where the thing is. So, for example, this graph that I have drawn in brown would have a different set of parameters than the graph that I've drawn in green. And that would have a different set of parameters than the graph that I've drawn in red. These parameters determine the features of the graph. They are all going to be these general shapes. Some of them will point up, some of them will point down, some of them will have this point as being a maximum, some of them will have this point as being a minimum. Some of them will have that point in quadrant 1 or quadrant 2 or quadrant 3 or quadrant 4. Or some of them might have that point on the x-axis or on the y-axis or at the origin. All of these details are determined by A, P, and Q. And by the end of today's lesson, if I give you A, P, and Q, you should be able to draw the graph without using a graphing calculator. So, A, P, and Q are called parameters, and they are numbers. So, for example, y equals 2x minus 3 quantity squared plus 4 is a quadratic function. And what I would say here, and we're going to go through specific examples, formal examples in your handout, but I'm just teaching off the cuff right now. And what this would mean is A would be 2, P would be 3, and Q would be 4. And what I would ask everybody to do right now is to compare this, which I'm going to refer to as a template, to this, and make sure you see how I'm able to determine that A has a value of 2, P has a value of 3, and Q has a value of 4. It's just a comparison, right? A is the number in front of the brackets. P is the number that we're subtracting from x. And don't try to figure out why it's minus. It is because it has to be, okay? And then Q is the number we add at the end. If I were to give you the following situation, I will stick with 2. If I were to give you the following, I hope it's clear that A is still 2. I hope it's pretty obvious we're comparing what I've got in red at the bottom of the screen to what I've highlighted at the very top. We are now comparing these two highlighted things. I hope it's clear that in this particular case, A is 2, Q is now negative 4. Because if you look at the top of the screen at what's highlighted, Q is the number that you're adding at the end. And I know we're subtracting 4, but subtracting 4 is the same thing as saying plus negative 4. Now, if you look at the green one, P was 3 because, listen very carefully because some of you are going to stumble on this. P is 3 because if I put 3 right here, I get x minus 3 and that's what I have, right? P here is negative 3 because if I put negative 3 in here, I get x minus negative 3, which is x plus 3, which is what I have written in red. So you're going to get used to, and I am admittedly jumping ahead a bit here, but you're going to get used to the fact that q will be the number that's at the end by itself, whereas p is the opposite of the number that's with x. A is simply the number out in front. All right, what else can we say about this? Well, a, p, and q are parameters, and the graphs of quadratic functions, these shapes that I drew over here, these are called parabolas. So the graph of a quadratic function is called a parabola. The shape is referred to as parabolic. And parabolas have certain features, like, for example, if you have a whole bunch of beams of light hitting and they're coming in parallel and they hit a parabolic mirror, they reflect to a common point. If you have a satellite dish at home, it's in the shape of a parabola because the beams are coming in from the satellite, they're reflecting off of that and reflecting to a common point. How many of you have a satellite dish at home? Has that arm sitting out in front with that thing at the end of it? That's the focus. That's where all of the stuff reflects to. That's where the signal gets concentrated so your magic box can de-scramble it and create an image. So they're called parabolas. The most basic quadratic function is f of x equals x squared. I want to write this out and demonstrate something to you. If I say y equals x squared, I can ask you what a is equal to, what p is equal to, and what q is equal to. And you should be able to tell me. It's a little tricky. How many of you have a pretty strong conviction that you believe you know what a, p, and q are? Only a couple. Craig, can you tell me what a is?
1.
A is 1. Excellent. What about p and q?
Both 0.
They're both 0. So if you don't see an a written, it's an unwritten 1. I could write y equals x squared as y equals 1 times in brackets x minus 0 squared in brackets plus q, which is 0. So the important thing is if you don't see an a is 1. If you don't see a p, p is 0 and q is 0. And again, a, p, and q are going to tell us something about the graphs. Today we're going to be looking at the features of this function and all variations or transformations of that function. And we're going to start off with the most basic one, which is f of x equals x squared. Don't forget, and I'm going to be slowly conditioning you to not having to write y. But don't forget that f of x is the same as saying y. So if I say, what is this second column? This second column is f of x. This second column is y. This second column is x squared because y is x squared. And we are only going to do this one time. I like to use, when I generate a table of values, these 7 inputs for the function. Whether it's a quadratic function or a linear function or maybe an exponential function or a cubic function, all these other functions you're going to learn about in the next year and a half, I use them. I don't think we need a calculator here. We're squaring x. An interesting thing about this function, well, I think it's interesting, is y will never be negative because y is found by squaring something. I was going to say y is always going to be positive, and that would have been a lie because when x is 0, y is 0, and y is not positive. But when I square negative 1, I get positive 1. When I square 1, I get 1. When I square negative 2, I get 4. When I square positive 2, I get 4. I hope you are understanding there's going to be what we call a symmetry to this graph. When I go over to negative 1 and I go over to positive 1, I get the same y coordinate. And what we're going to graph here is something that you need to just know from now on. That the graph of y equals x squared has a point at the origin, a point 1 to the left and 1 to the right and 1 up. Negative 1, 1, positive 1, 1. 2 to the right and 4 up. 3 and and to the left as well. 3 to the right and 9 up, which I think is going to take us here. So there's this idea of symmetry, and this is going to continue. And that is the parabola that is y equals x squared. I'm a heck of a lot better drawing shapes when I'm at a desk on a flat surface on paper. I can't usually draw very nice shapes on a vertical surface like this, but so I'm going to cheat a little bit. I'm just going to draw one side of it. And when you draw this, it's kind of like driving. I'm a little bit off up top, but I can fix that. It's kind of like driving. You should always be looking ahead at where you're going. Close enough. Right, so when I graph this, I was going through this point, but I'm also looking. I'm not happy with that. I'm going to do that again. I'm going to start here, and I'm going to look at this point, but I'm also looking ahead at where I'm going. That's close enough. We're not landing people on Mars here. We're just sketching a rough graph. And how I'm going to cheat is I'm just going to clone this and flip it left to right because I know it's symmetrical. There we go. So this is what y equals x squared looks like. I'm off a little bit here, but I'm just going to make the dots super big so that you get my point. And that's what y equals x squared looks like. Now we have to deal with some terminology. Well, the vertex is going to be the point that the graph is centralized around. So this is the vertex right here. And we usually use capital V to indicate the vertex, and the vertex here is at 0, 0. We are not graphing this on your graphing calculator. You're not. If at some point in time I want us to look on our graphing calculator, we'll do so. But I want you staying away from the graphing calculator for the time being. The axis of symmetry is a line. It's going to be a vertical line that separates the left and the right side of the parabola. This thing that I'm drawing is called the axis of symmetry. And the axis of symmetry is a line with this equation. Every point on that dotted blue line, the dotted blue line is not part of the graph, but every point on that dotted blue line has an x-coordinate of 0. Doesn't matter whether you're talking about this point here or this point here, these points all have x-coordinates of 0. The domain, wow, this is the first foray into domain and range this year. Domain, reminder from last year, is the set of all values of x that the graph has. And there's a number of ways to look at it, but I've been using this kind of analogy for a number of years. If I put my eyeball here, that's my eyeball, can I see by looking straight up a point on the graph? A point exists, right? At x equals 0, there is a point. If I were to go to x equals -2, is there a point at x equals -2? Yeah. What about everywhere between 0 and -2? Well, sure. Don't look at only this red point and this red point and this red point. All of these points, any point you can imagine on that line could be highlighted as a point. And speaking of point, the point I want to make is it doesn't matter where I put my eyeball x-wise, I will be able to see the graph. If I go over here to x equals negative, I'm going to estimate that to be -35, will I see the graph if my eyesight's good enough? Yes. It's going to be very far away, but it will be there. So what does that mean? It means that x can be any number, any real number. And we write that in a couple of ways. One of the ways we can write it is this way. This means x is an element of all of the real numbers. I don't want to get too sidetracked here, but there is a number set called imaginary numbers that we don't learn about in high school math. Non-real numbers. We could write instead the following. And this is not an x comma y. This is a situation where I'm telling you the first number is the minimum value of x and the last number is the maximum value of x. And I hope you remember doing that last year. Does anybody remember when you would put square brackets? Christy?
I thought if it was positive, like, or is like infinite.
No. It's not if it's positive or infinite.
Is it if the number is included?
Right. So if the number is included, if x can actually equal that number, you use square brackets. The reason why we don't put square brackets on the infinities is infinities are never something that x actually can reach, right? And we will encounter cases later where we have square brackets. The range, well, now what I'm going to do is I'm going to take my eyeball and I'm going to be moving my eyeball up and down. And I notice right here in that location I cannot see the graph. The first point I see the graph when I start floating above the floor is at y equals 0, and after that, I'll be able to see it. So what we could put here minimum y, comma, maximum y. And there you go. I didn't realize we'd be using that right away, but square bracket at 0 because y can actually be equal to 0. And I admit a lot of this lesson so far anyway is about terminology and how you write things, that kind of stuff. Now, this next bit of business is very confusing for students. First of all, we are going to be talking about minimum. A graph that looks like this has a lowest point. So when we talk about maximum or minimum, we're talking about the maximum or minimum of the function. And the function is y. So there is a lowest point for y here, right? Okay. The minimum value is y equals 0. Okay? That's the minimum value of y. When we say minimum of, we're talking about what is the minimum value. When we say the minimum is at, we're talking about where it happens. And that's talking about x. The minimum value of y equals 0 happens when x equals 0, in this case. The thinking here is that since x is a number that goes in, it determines the value of y. So when do we get a minimum value? When x is 0. What minimum value do we get? Y equals 0. Any questions with any of the details of that graph? Okay. Every quadratic function can be graphed or created by starting with that quadratic function and performing transformations. Stretches are transformations, reflections are transformations, and translations are transformations. And we're going to see all three of these today. And there's a whole first unit in Math 30 dealing with this. So let's take a look at the warm-ups to the next page. Warm-up number 2. Let's just not worry about A, P, and Q. What we're worried about here is taking y equals x squared and changing it to y equals ax squared. We're not including a P, we're not including a Q in any of these. And it says sketch the graphs. And we're going to use a graphing calculator here. But just before we do, don't get too far ahead of me here. You should know that y equals x squared goes through these points. And my recommendation is that if you want to see good curves, you're going to look at your graphing calculator. But if you just want to understand what's going to happen, you're going to do the following. We're going to graph y equals x squared with these dots. First of all, a has a value of 1. Would you agree the number x squared is being multiplied by is 1? Okay, let's fill in all of the a's before we do any more graphing. If I say to you, what about f of x equals 2x squared? Well, a is 2. 1/2 x squared, a is 1/2. Would you agree you're getting the gist here of how you determine what the parameter a has as a value? Okay. So I'm going to use different colors, but that doesn't help you. I'm going to use, I'll use green for this one. But what you can do, and again, I'm recommending you don't actually draw the curves unless you're very, very good at drawing curves. What I'm going to recommend to you is these are the dots you're going to use for 2x squared. That way, when you have all these dots up here, you can visualize what the graph looks like. And I'm going to use red for this one. And I think what I'm going to do lots of things here. I'm going to put little squares around those dots. And actually, before we get to the graphing calculator, let's just try this. The numbers are simple. If I were to look at 0 for x, and I put 0 into 2x squared, I hope it's clear I'm still going to get 0 even though I'm multiplying by 2. So this vertex of f of x equals x squared is also the vertex of this second graph, and it's also going to be the vertex of the third graph. All of the vertices, that's the plural of vertex, will all be there. Okay, let's take a look at x equals 1. When x is equal to 1, when x is equal to 1, x squared is 1 squared, 2x squared will be twice as great. This will be the corresponding point for 2x squared. And when x is negative 1, when we square negative 1, you get positive 1, but we have to multiply by 2. If I go over to 2, when I square 2, I get this point here, which is why that point is where x squared is. But now I want to say, where will 2x squared be? Well, I have to double that. 2 squared is 4, times 2 gives me 8. And what I'm getting at is what's happening is every point on x squared is being stretched away from the x-axis by a factor of 2. It's being moved twice as far away from the x-axis as where it was on x squared. So what you're getting, and we will look on the graphing calculator in a bit, is something that is considerably taller or narrower. Okay? And I don't want us to get hung up on precisely how much taller or narrower it is in this course, but it's twice as tall because a is 2. If I were to take a look now at the third one, well, I want to take x squared. When x is 1, x squared will be 1, but I now want to multiply it by 1/2. I'm just going to put it there. And this will happen on the other side as well. What about when x is 2? Well, x squared is 4, but I want for the red function 1/2 x squared. So now it's not twice as far away from the x-axis, it's half as far away. And the result is that this is, we still use the word stretched, but don't worry about that. It is stretched by a factor of 1/2. You can say squished if you like, okay? You can say compressed, but in Math 30 we use stretched. So let me throw these all into the graphing calculator at the same time. I would like you to use the same window settings as me. So you're going to go to your graphing calculator and hit Window and set it up so it matches what we have here. We're going from You know what? Let's go from negative 3 to 3 for x. So I'm going to go negative 3 to 3. For y, I want to go from, say, negative 1 to, let's go up to 9 for y. It's kind of matching the same grid that we have in the handout that I've given you. And for y, I'm going to put x squared. I'm also going to put 2x squared. I'm also going to put 0.5. I'm not a big fan of fractions, but I think it's easier to just enter 0.5x squared rather than a half x squared here. So I'm going to hit graph, and we're going to watch what happens. Here's y equals x squared. Here comes 2x squared. It's taller and narrower. Here comes a half x squared. It's shorter and wider. Are you with me? Would it make sense that if I had 3x squared, it would be even narrower and even taller? Sometimes I enter x squared that way. You're just going to have to live with it. X times x. I hope it would make sense to you that something like 0.1x squared would be very, very flat. Because it's really, you're taking x squared and you're multiplying the vertical distance by 10%. 0.1 is 10%. All right? Okay, let's move on. Look at warm up. B. And there, you should say a B. It doesn't, though. I don't think a B printed there for some reason. I don't know why. Notice where the x-axis is here, and we're just going to go ahead and use our graphing calculator. I don't even know that we need to sketch this, although I will put the points down for you to draw if you like. Let's set up our window settings to match this. I'm still going to go, let's go from negative 3 to 3 for x, but this time let's go from negative 9 to positive 1 for y. The x-axis is up here. So I'm going to go from negative 9 to positive 1. I'm going to go into y and clear out everything. And I'm going to graph negative x squared. Maybe before we do, if y equals negative x squared, what's a? 1? Negative 1. Negative 2, negative 1. Do you see the only difference here is that these a's are negatives? How many of you suspect you know what's going to happen here? It's going to be flipped over. Instead of x squared going like this, x squared will go like that. Well, let's just check that one out to begin with. Y equals x squared graph. Well, not what I wanted to enter. Y equals negative x squared graph. Yeah. And you know what? If you don't change your window settings, please. If you graphed x squared and negative x squared on the same set, there's negative x squared, there's x squared. I hope you understand it's the same shape. It's just upside down. And we can put in the other ones to confirm what I suspect many of you know. That the only difference is, I've got my window settings backwards. Give me a second. I want to go from negative 9 to 1. The only difference is the 2x squared is negative 2x squared, so it's still narrower and taller, but it's upside down. And the negative 1/2 is still shorter or wider, but it's upside down. I don't think we need to plot the points. One of these days I just need to change my handout so we don't have to plot them. You have your graphing calculator to learn from here. What is the rule? What's going on here? Well, the following is true. If a is greater than 0, the parabola opens up. And opens up is a way of saying it has this appearance to it. So if the number in front of the x squared is positive, it opens up. If the number in front of x squared is negative, the parabola opens down. And I'm going to choose to explain the rest of this with A in a different way, and I want to really highlight something to you. What I'm about to tell you about A, to summarize how wide or tall or narrow or short these things are, is not something that you need to know exactly. You need to know in general the following. If you were to look at a number line for A, and here is A equals 1, and here is A equals -1. This is for A. What we're talking about, I better put 0 in here as well. What we are talking about in this region, first of all, let me be careful here. I need to just change something. What we are talking about in this region are parabolas that open up. I included just an empty circle at 0 because you can't have A equals 0. If you have A equals 0, there's no function. Okay? So that's what's happening here. On the other hand, if you have this, the parabola will open down. And that's what I've got above, right? But what I need you to understand is that as you go to the right of 1, the parabola becomes narrower and taller. It gets squished this way. And as you go to the left of -1, the same thing happens. It's just in the opposite direction, right? However, in here, the parabola is wide or short. And again, in Math 30, we get into the details of exactly how wide or short or narrow or tall these things are when we apply this to any function. But I think that's what you need to understand. That if you're looking at A equals 5, it's a parabola that opens up and it's really, really narrow. If you have A equals -0.1, it's a parabola that opens down because of the negative, and because A is 0.1, it is really wide. All right. Let's explore what Q does. And again, I'm going to do this on the graphing calculator. Do me a favor, please, and for these 1, 2, 3, 4, 5 different functions, write down the value of Q for each one. Actually, I'm not going to use a graphing calculator. I have this one loaded up in graphing software. And I'm going to do my best here just to explain briefly why what's about to happen is going to happen. If you calculate the y value here, then you take x squared and add 2. Okay? But listen very carefully. In this second function, x squared is the y coordinate in the first function. And you're just going to add 2 to it. So every point on the first function is going to have a y value that is now going to be increased by 2. What do we learn here? Let's take a look. There's x squared. There is x squared plus 2. And it might be a bit of an optical illusion, but that red graph shifted up 2 gives you exactly that blue graph. I know it doesn't quite look right because the lines are getting closer together, but just to demonstrate to you that it is true, if I take this red graph, and I made the mistake of choosing my highlighting tool, so we'll just wait for a bit here. There, that was quick. And I shift it up to, it matches the blue one perfectly. What do you suspect then x squared plus 5 will look like? We'll shift it up 5. What about x squared minus 3? Down 3. Now we can confirm all of this, and then we'll write a rule. I'm going to get rid of the x squared plus 2 and just put x squared plus 5. Yep. Shifted up 5. X squared minus 3. Shifted down 3. X squared minus 7 shifted down 7. So what do we conclude? Well, I want to do my level best here to write a conclusion that is succinct as possible. I don't want to write a big paragraph here. Okay? There is a vertical translation of, now I don't want to say one thing if it's up or one thing if it's down. I just want to say of q units, period. You have not been formally taught what those two vertical lines around the q mean. Does anybody know, though? You might have encountered it in chemistry. No, it's not a fraction.
Absolute value.
Good. It's called absolute value. And what it means is we don't care about the negative. So if Q is 4, the vertical shift is 4 units. If Q is negative 4, the vertical shift is 4 units. It means don't worry about the negative. But now we're going to say up if Q is positive. If Q is positive, it shifts up. That makes sense. Positive means up. And down if Q is negative. By the way, I could have written here this. I could have written here that. So now we know what Q does. It shifts the parabola up or down. Let's figure out what P does. So this is going to be a little tricky. This is where everything is going to go along great. You'll be walking down the street whistling and you're going to start stumbling. You're going to be making mistakes from time to time, and it's natural. First thing I want everybody to do is for all of these functions, I want you to write the value of h. We are comparing this, let me explain something to you. If I ever call ph, and if I ever call qk, it's because we don't use p and q in Math 30. We use h and k. All right? Just so you know. We're going to be comparing these to x minus p quantity squared. And I want everybody to write in the value that p has for each of these 5 quadratic functions. So this isn't the part you'll stumble on. You'll get used to this very quickly. Since it's x minus p, if I have x minus 2, then p is 2. Right? If I had x minus p quantity squared, and I want to get x plus 4 quantity squared, the reason why p is negative 4 is x minus negative 4 quantity squared gives you x plus 4 squared. So p is the opposite of the number you see in the brackets. Now, let me get these graphs going here, And it's really quite surprising if I were to take a look at x squared. I'm going to graph x minus 2 quantity squared. What do you think the graph of x minus 2 quantity squared is going to look like? I want to write this down so you can see what I'm talking about. That's x squared. I'm interested in what this is going to look like. What do you think it's going to look like, Nate?
That is x minus 2. You click x minus 2 squared over.
Oh. Wow. The cat's out of the bag then. That's x squared. What do you think x minus 2 squared is going to look like? Most people would say shifted to the left because of this minus 2. But it's not. It's shifted to the right. But wait a minute. Let's see if you can pick up on this. X minus 2 quantity squared is x squared shifted to the right, and p is positive 2. Positive is to the right. On a number line, positive is to the right. If we take a look at x plus 3 quantity squared, p is negative 3, right? Should be shifted then to the left. We're basing our decision not on what's with the x, but the number p itself, whether it's positive or negative. And I can show you that when it's x plus 3, it's shifted to the left 3. There's a reason for that, and I don't want to get into it in today's class. There's a reason for there being kind of an opposite nature to the x that we don't have to worry about with the y. So what do we learn? We learn that there's a horizontal translation. Left, right is horizontal. H, there it is again, p units, and it's either going to be to the left or the right, and whether it's to the left or the right depends on whether p is negative or positive. Left if p is negative, right if p is positive. Are you with me on that? What we have to do now is be able to put it all together, along with the terminology, and we're going to learn one more thing. So, this is not that big of a deal in this course, but if you were to ever apply these transformations to a quadratic function on paper, you do the stretching first, keeping the vertex at the origin, and then you shift it around. That's all. So for all of these, describe how the function can be arrived at from f of x equals x squared. Sketch the graph of the function stating all of the features. Okay, so a is 4. Let's start there. Will the graph of this function open up or down? Up, because a is positive. Will the graph of this function be the same width and height as x squared? No. Will it be taller and narrower, or will it be shorter and wider? Taller and narrower. So this is the part that I really don't care about. But if this is what x squared looks like, then we have to draw something that's narrower. Okay, that's all. We don't have to worry about precision here. Would you agree then, and I don't want you to draw this just yet, that forgetting about p, which is 7, and q, which is 6, would you agree that the parabola would look something like this? It's narrower? Okay. The vertex right now is at 0, 0, yes? What does p equal 7 do now? Shifts it 7 units which way, Ashira?
Right.
To the right. And what does the 6 do? 6 units up. Think about this for a second. I'm going to take this graph, and I'm going to shift it 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. The vertex is going to be at 7, 6, which is P, Q. The vertex is always going to be at P, Q, because P tells you the x-coordinate of the vertex, since P tells you how far to shift and in what direction. Q tells you the y-coordinate of the vertex. There is a graph of the function, a very approximate graph, and if you wanted to, as a comparison, you could certainly put that in there just to show that the one we drew is narrower, but that's not important, okay? It really isn't. What are we asked to do here? Let's take a look. We are asked for a description of how we arrive at that. Well, we already did that. I'm not writing an exam, and neither are you. On an exam, you would write, it is stretched so that it's taller, and then it is shifted 7 to the right and 6 up. We don't need to spend time writing that down. What else are we asked about for this question? We are asked the direction of opening and whether it has a maximum or minimum value. Well, it opens up. There's a minimum value of at, what is the minimum value of the function? Who just whispered that? It's 6. The minimum value is the minimum height, and height is a measurement of y. The minimum value of y equals 6 at, where does that happen? When x equals 7. Just a second here. This is Q, and this is P. And with a little bit of thought, you will realize that it's always going to be that case. If it's a minimum. It could be a maximum, right? Things could be flipped over. Domain. Well, x is any real number. Range, looking at the graph, y is greater than or equal to 6, which, by the way, is Q. I don't know where this lesson is going in terms of completing the lesson and giving you an assignment. Don't worry about that. If we just spend the rest of the class, the last 15 minutes, finishing the lesson so you get a good understanding, then that's fine. We have time. What else? Coordinates of the vertex. I already wrote that down. And again, I'm trying to draw a generalization here, which is that the vertex will always be at P, Q. I'm trying to get you to understand that there will always be a minimum if A is positive, because if A is positive, it opens up, so there's a lowest point. What else? Equation of the axis of symmetry. Well, the axis of symmetry is this, which would be x equals 7. Oh, well, that's P. The axis of symmetry is at x equals P, because P is the x-coordinate of the vertex. What else we got? Oh, sketch. We're done. And I think for most of the rest of these, I'm not going to write down a lot of stuff. We'll write down some things, but I think you're going to be getting the idea. If you take a look at this, A is negative 1/3, P is negative 4, Q is positive 7. Can we just mentally digest those three statements and make sure that you agree with them? So if y equals x squared looks like this, what general shape will this function have? What are two differences that this function will have with an a value of negative 1/3. Yep. It'll open down and it will be wider. So this graph, forget about where it is, this graph is going to look like that. Now that might be an exaggeration, but this is why I told you earlier I don't care about the specifics of it. Okay? Where will it be? Well, again, I don't know that you need to do this. You take y equals x squared, you flip it over, you make it wider, and then you shift it for the left and 7 up. The vertex is going to be at negative 4, comma 7. You can answer all of the questions now. Domain, any real number. Range, y is less than or equal to 7. Axis of symmetry, x equals negative 4. Max at y equals 7 when x equals negative 4. I think that's it, isn't it? It's certainly in the important stuff. I mean, you could say it stretches to make it wider, and it reflects and it shifts, but that's neither here nor there. Are you getting the hang of this? All right. First question. I want everybody to write down the coordinates of the vertex. Where will the vertex of this be? And the answer will be at 3, comma negative 8 is correct, because P is 3 and Q is negative 8. So this is always here at P, comma Q. So the vertex will be someplace here. Will this parabola open up, Carly, or open down? Excellent, because A is positive. Will this parabola be narrow or wide? Excellent, because 0.2 is a number smaller than 1. So this is going to open up, and it will be quite wide. This is at 3, comma negative 8. And, you know, it's not that I'm tired. It's not that I'm being lazy. I think this is easy now. I think for you to say the range is y is greater than or equal to negative 8 is basic. The domain is x is any real number. There is a minimum value of negative 8 for y when x is 3. The axis of symmetry is x equals 3. Are you with me on this? Okay. And last one. Yeah, and we're gonna keep to the schedule here. You're not gonna have a lot of time, but I think the basics of this assignment you can do every second question, I think, and still be on top of things. And by the way, I always have a quiz the next day on this. Okay? And the quiz would pretty much be like these questions. Owen, does this parabola open up or down?
Down.
Excellent. Would it be a narrow parabola or a wide one? Don't know? Because the A is 4, forgetting about the negative, because A is a big number, it gets taller. And that's the thing to think of, is A is kind of a measurement of the height. So when we say taller, I saw somebody kind of say narrower. Narrower and taller mean the same thing. So this will be opening down and it will be narrow. I mean, this is quite an exaggeration maybe, but it's going to have that general shape if x squared looks like that. Where will the vertex of this be? Well, P is 5 and Q is negative 12. Is that the same as the one in your handout?
Yeah.
Number for number? Okay. So it's going to be at 5 comma negative 12. And you should be able to answer anything about it, like where's the vertex? 5 comma negative 12. What's the equation of the axis of symmetry? X equals 5. What's the maximum value of y? And there is a maximum because it opens down. There's a top to the hill. The maximum value of y is negative 12. Where does it occur? It occurs at or when x equals 5. Domain, always any real number. And range, y is less than or equal to negative 12. That's it. And I think next time I teach this, just so you know, I don't think we'd even use a grid. We'd just go with the graphing calculator and learn the rules. So